Hello guys and welcome to my YouTube channel. In this video, I'll be demonstrating a chemiluminescence experiment involving luminol. If you are a chemistry student, you might already be familiar with it, but I'm also going to be showing you how you can change the color of the glow using fluorescent dyes towards the end of the video. So stick around and let's get started. The first thing that needs to be covered is the materials required. Don't worry about the measurements, we'll be making them along the way. You can pause the video and take a look. Also, this is an image that you can refer to for the same. Wear latex gloves if you want to be safe. And I recommend labeling your beakers, especially if you're going to be repeating the experiment, so you can keep track of them and make sure you don't mix any unwanted chemical. And tear your weighing scale with the watch glass. The first step is measuring 0.1 grams of luminol using the watch glass and weighing scale. We're gonna grab a luminol bottle and spatula and scoop some out. Place it on the watch glass and wait till we've got the right measurement. After this is done, we're going to grab our first 100 ml beaker. This will be for solution 1 and scrape off the luminol powder from the watch glass. Make sure you get every last piece of luminol that you can see, because even small pieces stuck to the watch glass make huge differences at this scale. Keep scratching it off, and if you can't get an accurate measurement, I recommend adding a little more luminol than maybe 0.1 grams when you're going to be measuring, because some will always be left on the watch glass. And the same thing goes for measuring liquids in measuring cylinders. Speaking of which, our next step is measuring 5 ml of sodium hydroxide in our first 10 ml measuring cylinder. Also remember that this is a 1 mole solution. If you have a different concentration, you can adjust for the volume. And this is why latex gloves come in handy. So let's pour. We're gonna pour this measurement into our beaker, and using our glass stirrer rod, we're gonna make sure every last piece of luminol powder has dissolved in the sodium hydroxide. We're gonna stir it thoroughly. Now that that's done, the final step for preparing solution 1 is measuring 45 ml of distilled water in our 50 ml measuring cylinder. And then we're gonna mix it in the beaker. That's it. Now we're gonna move on to solution 2 in our second 100 ml beaker. So our first step for preparing it is measuring 10 ml of hydrogen peroxide, and remember the concentration is 3%. So again, you can adjust for the volume if you have different concentrations. I'm gonna grab our second pipette that we're gonna use for the hydrogen peroxide vial and measure it in a 10 ml measuring cylinder. Another one. Second one. And we're going to pour it into the beaker. Now for the next step, that is measuring 10 ml of, again 10 ml of potassium ferricyanide with a concentration of 3% as well. Um, in You can opt to use another measuring cylinder. Obviously you're going to be using a different pipette, since we don't want to be dipping different chemicals in their storage, in their respective storage vials. But if you're confident that you won't contaminate the pipette that you're going to be placing into the vial by touching it to the sides of the measuring cylinder, then there's no problem if you want to use the same one for hydrogen peroxide and potassium ferricyanide, since we're anyways going to be mixing them. And we mix it in the beaker with our hydrogen peroxide. Now the final step for this is measuring 80 ml of distilled water using our 100 ml measuring cylinder. And finally mixing it in with our potassium ferricyanide and hydrogen peroxide. Now that we're done with both our solutions, we'll keep them side by side and we're ready for the final show. So we'll grab our 250 ml beaker and we're gonna mix these two solutions together. Note a cyan glow emanating from the solution. Now moving on to the scientific explanation, we're going to introduce our chemical of focus, that is luminol. So luminol is an organic pale yellow crystalline solid that is only soluble in polar organic liquids. Its full IUPAC name is 5-amino-2,3-dihydrophthalazine 1,4-dione, and the shortened version is 3-aminophthalhydrazide. When dissolved in a neutral solution, the relatively acidic hydrazide and basic amino groups makes the substance bitter ionic. The pi stacking intermolecular forces generated by the aromatic ring present in its molecule contributes to its solidity at room temperature. And now getting on with the reaction mechanism. Thanks to resonance making it relatively acidic, when luminol is mixed with a sodium hydroxide solution, it engages in a neutralization reaction to create a water dissociated form of the sodium luminol dianion salt. The resonance between the oxygen and nitrogen atoms introduces two tautomers of the compound, one being the less stable keto form and the other being the more stable enol form. When hydrogen peroxide is mixed with this solution, it decomposes to form gaseous oxygen dissolved in the water. In the presence of an ion containing ionic catalyst such as potassium ferricyanide, which is being used in this instance, the O2 reacts with the two ketone groups to create an intermediate cyclic peroxide. The peroxide's bonds with the ketone carbon atoms forces them to lose any double bond with an adjacent atom, causing the double bond to shift between the nitrogen atoms and the negative charge to move to the ketone oxygen atoms. As the oxygen atoms attempt to form resonating double bonds, the nitrogen atoms lose their bond with their respective ketone carbon atoms and are ejected to form gaseous nitrogen. The two oxygen atoms of the peroxide take their place and break apart to enter resonance with their respective ketone, resulting in two carboxylate groups attached to an aniline. The final phase of the oxidation makes bonding electrons involving the new oxygen atoms enter their ground state, resulting in the emission of electromagnetic energy in the range of visible light, which can be seen as a cyan glow. This transition from a higher to a lower energy state of the same chemical species is referred to as intersystem crossing. The final product of the reaction is a solution of sodium 3 aminophthalate and potassium ferricyanide. So you can take a look. I'm assuming that you've referred to this chart for the same. Um, that's the mechanism. And now the next thing we're going to move on is the fluorescent extent. We're going to move on to the fluorescent extension. Um, Over here, I've used pink dye. Um, it's not very bright, which is the reason why, in my opinion, this is the this is a better example. I used yellow fluorescent paint. It's brighter. So now moving on to the mechanism behind fluorescence. Fluorescent compounds are capable of absorbing higher frequency light and consequently re-emitting it at a lower frequency. Conjugated pi bonds give their molecules this ability. Since the electrons involved in this weak bond are very mobile, they can enter higher energy states by absorbing electromagnetic radiation and immediately re-emitting it. Typically, the longer the chain of conjugated bonds, the lower the frequency they can emit. This allows certain compounds such as fluorescein and rhodamine red to emit visible light when exposed to a high frequency ultraviolet light. When exposed to the blue light emitted by the luminol reaction, such compounds can cause the solution to glow in different colors owing to these properties. So again, you can refer to this image for the same. That's all I could find. Um, and yeah, that's it for this video. Thank you for watching. Hope you found it useful. Hope you enjoyed it. And maybe I'll see you in the future.